Hello friends, in this video we will see about equivalence relation on a set. This is very important because in most of the times G by H, this is right, AH such that A belongs to G. This relation, people say that A related to B if A V inverse belongs to H, where H is a subgroup of G. This is an equivalence relation. I can give hundreds of examples, but I will give one or two. A related to B, AB belongs to G. If A there exists G belongs to G, AG G inverse equal to B. This is called conjugation relation. This is an equivalence relation, and we can put many relations in group, in many structures in topological spaces, which is turned into the equivalence relation. And that's why this notion of equivalence relation is very important in mathematics. So here we will see equivalence relation and how to deal with function of equivalence relation. I mean, there is a relation between function and equivalence relation. That's what we want to say. Okay, so the idea is this: let A be a non-empty set, be a non-empty set, then there is a relation. A relation means what? It's there is a binary operation from A cross A. Let's say it's a subset. It's a R subset in A cross A, and binary relation is, let's say, A related to B. It's like that they write A related to B. Okay, for A B belongs to R, like this. Some relation, that relation is set, is a binary relation, and we set to be one reflexive if A related to A. I mean, it's a relation means it's a subset on A cross A. It's like I will give you example and you will understand. Okay, A related to A, then for all A belongs to A, it's reflexive. That means in the set consists of this set R consists of A comma A inside R. This is idea. Okay, transitive if not transitive. Okay, that's the third property. Transitive, A related to B and B related to C implies A related to C. That means if this set R consists A comma B, B comma C, that implies A comma C will be there in R. So second property, symmetric relation if A related to B, if and only if B related to A. It's called symmetric. It means the set A comma B belongs to R implies, in fact, if and only if B comma A belongs to R. Okay, so if these three properties satisfied, and we will say that is a equivalence relation. Why this is called equivalence relation, we will see at the moment. We will see now. It's a sort of a very nice exercise that you can see some of the relations are not equivalent. Try to find it. Okay, you take a group of people in the, let's say, apartment, group of people, and a group of male. You take group of male and define like a male is related to other if he is father. Two male related to other if he is father, otherwise not. You see this relation satisfies these conditions. And similarly, you take a group of people and you define like this: a people related to another people if he is some relative, blood relative. And you see this reflexive, symmetric, and transitive things are satisfied. And in this way you can produce more and more example. Okay, so we use this symbol for relation, the equivalence relation and this thing. Okay, and let's see, if we have a set with a relation, then we use this standard like set A belongs to A. What does it mean? A, the class, we call this as class or equivalence class of A, that is set of all x belongs to A such that x is related to A. Suppose we have equivalence relation. Okay, suppose we have equivalence relation, and see, let's say what happens here. Suppose I have A, then I have a small a, let's say many people are there, let's say here many people in the set is there. Then I take an A, I will connect this relatives and I am taking out. So what's happening here, this is capital A, so I'm splitting A relatives, A and its relatives. Okay, then there will be some B, its relatives, C relatives, like that I'm splitting. Okay, you can ask why this is disjoint. I can split the relatives. We will see that it is disjoint. Disjoint means A can be written as this is a symbol for disjoint union, that is union of I belongs to some index set, it may be finite, infinite, doesn't matter. AI intersection AJ equal to empty if I not equal to J. This is technically writing, but what is happening here is this one, this picture is happening. Okay, you'll see that why. We will take a set with the equivalence relation. Let's take relative of A, that means set of all x belongs to x is related to A. This is the equivalence relation, remember. So let me take another B. This is a set of all y belongs to y related to B, right? Now I'm saying that either A equal to B or the intersection is empty. Why? Let's see. In the case suppose A not equal to B, that is there exists x belongs to class A but x does not belongs to class B. We can say that it may be possible if you assume that this is maybe possible, but in the case we assume that in the reverse role play, suppose A is a subset, then there exists a one guy in this class B will not in the class A. So we can assume that I didn't really make any ordering, so we can, without loss of generality, you can assume that A inside the class or x inside class A but x does not inside class B. That means x is relative of A but x is not a relative of B. Okay, so in the sense you cannot, if A intersection B not equal to empty, then A is relative, let's say let y belongs to here, A is relative of y and y is relative of B. By transitivity, A is relative of B, so B will be inside the class A because I'm collecting relative. Since B is related to A, then all relative of B also related to A, so the total class will be in A. In vice versa, A related to B, so every relative of A is related to B and this containment will come. So class A equal to class B when this is precisely not empty. From that it's clear that class A equal to class B or class A intersection class B equal to empty. So that's why the capital A, the set is splitted like this, disjointly. It's like disjointly. So upshot here, whenever you have a equivalence relation, then that relation splits. This is a symbol we use. This is the union of AI. Any indexing set, finite, infinite, uncountable, countable, doesn't matter. This means AI intersection AJ equal to empty if I not equal to J. I comma J belongs to the index set. Just indexing. Most of times subset of natural number used. Okay. So upshot here, whenever you have a equivalence relation that splits the partition. Now the reverse way, converse. Suppose I will have a partition. Can I get a equivalence relation? Can you define a equivalence relation? Partition means this is union AI. I belongs to I. And can you define a equivalence relation? Yes. How? Let A comma B belongs to A. I am saying that A related to B if A comma B belongs to AI for some I. If such thing happen, exactly one I, because it is partition, right? For some I. So let us check this is reflexive or not. Suppose A belongs to some I, then A related to A, right? Because A inside AI, so A inside AI. So reflexive is done. Symmetry, let's say symmetry. A related to B implies A comma B belongs to AI. So that means B comma A belongs to AI. So B related to A. I mean B related to A. So this is if and only if, all statement. So third, transitive, A related to B and B related to C, that implies A comma B belongs to AI. Since remember this, the B belongs to AI and this is a partition. Partition means they don't overlap. The set don't overlap. So and B comma C belongs to AJ. From here I am writing this. From here I am writing this. Okay, but you remember that AI intersection AJ equal to empty or AI if I equal to J. Here there is a non-empty sense, so I must be equal to J. So that means A comma B comma C belongs to AI, that is equal to AJ, because non-emptiness. B is common, no? Okay. So finally A comma C belongs to AI. So A related to C. So from here you can say that whenever you have a equivalence relation, we can split. Whenever you have a partition, you can get a equivalence relation, and this is very important. So finally, how to compare with these functions? Okay, this is very important. This is going to be very important in later on subjects. Let f is a function from A to B. Let's say surjective. This symbol we use for surjectivity or onto, both are same. That means every element here has a pre-image. Okay, so I'm going to define a relation. I'm going to define a relation in A, like A related to B if f of A equal to f of B. See, this is very important because it's fundamental theorem, you know, right? Surjective homomorphism, then G by kernel of, let's say, phi. Here is isomorphic, that phi delta they will define. Now this kind of things are comes from here, this partition idea. Okay, A related to B if image goes to the, images are same. That means I have A here, I have B here, and two elements are, I am saying that relative if they go to the same image. They go to the same image. Okay, so let's see this is the equivalence relations or not. A related to B implies, is it A related to A? That is true, right? F of A equal to F of A. Function is a unique rule to assign a element to the unique image, right? But here anything can have a many pre-image, but here every element has must be have one image. So A related to A. Okay, let's say A related to B, then f of A equal to f of B. That is same as saying f of B equal to f of A, right? Both are same, and that is same as saying B related to A. This is reflexive is over, symmetric is over. Now we will prove transitivity. Transitive. How? So A related to B and B related to C. That means from here I can write f of A equal to f of B. From here I write f of B equal to f of C. So from here I can say that f of A equal to f of B equal to f of C. But all I wanted f of A equal to f of C. So from here it's clear that A related to C. So transitive also over. So finally what we are getting, whenever you have A, B surjective map and that defines a relation, and conversely, let's say I have a relation, shall we get such B, and that is also possible. Let's say B equal to this thing, the class, okay, I have a relation, right? Then you take the class, that means A is like class, okay? So it's a subset of a power set of A. I'm just taking the classes, okay? This is A, like this. Here you see I'm taking, this is a one element, this is a one element, this is one element, this is a subset of power set of A. So it's a set. Then I'm defining A to B function. I'm defining f of A goes to class A. This is surjective. Why? Because what is B? B is taken like a class A such that A belongs to A. So every element of B is led by a representative A. So that means any element here is like some X. So you have a pre-image X. So this is a surjective function, and this is well defined because X equal to Y implies f of X, that is class of X, f of Y, that is class of Y, and X equal to Y, this is equal, right? Because class of X and class of Y equal to, because X equal to Y, both classes equal. So this is well defined function and surjective function. So finally, upshot, what you wanted to understand is equivalence relation is nothing but giving a surjection map. I wanted to define an equivalence relation of A. It's nothing but giving a surjective map to the B, and this is what you wanted to understand. Okay, this is many places you can get this ideas. For example, let's say real number to S1. I want to talk about 2 pi periodic function. You can like 2 pi periodically you can split like x goes to e power 2 pi ix. Okay, this is a surjection map. Whenever you have a surjection map, you have a split. Whenever you have a partition split, you have a surjection map. This is how it's defined. Okay, so finally using these ideas you can go many places. So equivalence relation is really giving a surjection map to the another set. Okay, that's what you wanted to get. This is a basic of set theory which I wanted to go through, and many places you will see